which means that we are supposed to be we already passed the mid-autumn, and we are now getting to be kind of a later fall, okay, not totally that, because it will still have 30-some degrees temperature. But I know that for some of you are from more southern area than Taiwan, that for you, probably that you feel that it's getting colder. But I have known many friends that they are from more northern area. They say, what season change? And they don't feel any season change. We still have 30-some degree temperature. And I think this coming weekend, there will be yet another typhoon. Right now it's developing in Philippine area, and it's going to pass by Taiwan again. So, during the weekend, and also early next week, that we're going to have maybe again some rains. Probably not a typhoon directly. Okay, we have posted homework 2. Okay, and later today, I would talk about this homework 2. But just in case you are not aware of it yet, okay, we have posted this homework 2 assignment, and also there are 3 different files, okay, and you are supposed to look at the project, which is trying to look at one of the most popular data set, which is the MLIST, okay, and then try to implement using MLIST kind of a network and try to handle fashion MLIST, okay, and also then try to see that how you can combine the data sets from 2 different domains, and maybe see how, whenever you have a model and when you need to try to handle the data set from some totally different area, what can we do? Okay, we don't always need to retrain everything from scratch. We should be able to reuse a lot of result already produced for other areas. Okay, but today still that we want to talk about some topics first to complete our knowledge on building the neural networks. Okay, so we've been seeing this picture for many times, and the idea here. Sorry, let me turn on the recording. Oh, you have recorded? You saw this? Oh, okay. So we have seen this motivation of trying to do machine training. Say, for example, suppose that you have some training data set, which is the xi, yi. Xi is a whole vector or tensor of numbers, and you have the yi, which is supposed to be the predicted label or correct answers. And our idea is that to build some kind of machine learning model, which will be using the idea, using F as the name of this model. So inside the model, we have the parameters or the weights, W, okay? And the idea is that F, the model itself, the architecture of the model will be predetermined by whoever designed the model. So we don't change the model itself. However, the W will be the weights inside of the model can be trained or can be improved or can be adjusted according to your input data set xi, yi, okay? So the idea is that we are trying to update this W using the training data set. And when you run the input data xi, the training data xi into F using the current W, you will produce the loss, which is how far they are from the current correct result of YR. Okay, so from the data loss, which can be defined in many different ways. So for example, here you can see that we have the softmax definition, we have the SVM definition, which are always comparing between the correct result and your current result and see how much you are the current result is deviated from the correct result. Okay, so from the data loss, then we usually would add another term which we call the regularization loss, which is to describe how the weights, how the shape of the weights or some property of the weights can be revealed by using some R function to say that how good it is to be, suppose that we have the most ideal weight, okay? And so combining these two, we can come up with the current value of the loss given some instance of the W, which is given some weights, current weights in this model W, okay? So from the loss, then we try to see how we will be able to use that information to help us tune or update the W, okay? And you can see here that we have shown you this specific method, which is called the gradient descent, okay? The idea here is that the weight, okay, whatever the current value of the weights, you'll produce the loss function of loss value. And we can visualize it just like we are trying to walk in the terrain with a lot of W values, and each of the W value will produce us what is going to be the current height or current values of your loss. And we want to be able to minimize the loss. The loss probably wouldn't be zero, okay, even you have a very, very good model, because you don't know what kind of value you will see in the future. But given the current input training data sets, we can try to imagine that there are many different possible values, weights in the W, okay? And when we try to update each of them, it's just like we are updating our current positions in this big W. So each of the W1, W2, W3 can be imagined to be one dimension in this terrain. And whenever you update that to a certain different area by moving up and down to the left and right, okay, or doing some other things in the hyper space, okay, it will produce one particular loss function, and we want to be able to minimize the loss as much as possible. And we'll be searching for that minimum point, just like walking through the terrain. And eventually, if we can reach the global minimum, okay, that would be, given that particular loss function, then it will be our final, kind of results, okay? So here you can see this is kind of in general, the overall structure of doing the machine learning training is that we just keep on using whatever data we can have. Here you can see the data, okay? And the data here originally is defined to be the whole input data, the training data set, okay? So for each training set, we find the loss function and we give what is the current weights in the W. Then from the loss function distribution and the weight and data, okay, then we will evaluate what is the current gradient, meaning that which particular angle we should be moving along. Okay, what will be the suggestions from the terrain to say how we should move in order for us to try to reach the minimum point. So once we have computed the weights gradient, then we can simply say, oh, the current weights should be updated because we want to move to different locations. So we just adjust every individual weight according to this weight gradient. And then we use the step size to say, well, we know that here we should go this way, but we don't want to jump to a new location too much. So we simply use a step size to say, let's just make a little bit of adjustment and see how it goes. Okay, so by doing this repeatedly using a loop, then eventually, when we reach some, say, for example, some criteria to say, that's good enough, we should stop. Then we can stop this training. Okay, so finding out the gradient in any particular location, okay, originally is to say that, well, yeah, you can try to search through all this, terrain and when it will be here, which way, specifically to go. But it's a very time-consuming process. It takes a lot of energy if you have a lot of training data. Okay. So here we can try to use some mathematics to find this, or we can try to use some computer way. Okay, not to use the mathematics, but simply say, well, I don't know which way I should go, but I'm just going to explore all the neighbors I have. I'm currently here, and if I change W1 for some value, or change W2 for certain value, and W3 for each, try each of that, okay, and then see how the difference will, how the change any of this, the Wi will change the loss function. Then we just try each one of them, okay, and then take the average of that, okay, and then find out to see that, okay, which particular direction would give us the best kind of a result in order for us to reduce the loss, okay. So we can try to explore all of them, all the Wi, by changing them a little bit here and there, okay, among all the data that we have, taken all the data into account to see that how they will change. But there will be a lot of computation because you have n input data sets, okay, and n data items in the input data set, then it will take a long time. So usually we don't do that. Usually we would just take some mini batch, okay, from the n. Say, for example, you can say, I'm not going to look at 10,000 pieces of data. I'm going to look at only 32 or 64 or 128, okay? And by taking a subset of the data for your training, okay, and every time it's going to be randomly, then you will also be able to compute some kind of gradient to give you some idea which way you should move. But you are not, because you are not taking the complete data set, so you are limiting yourself to be, say, for example, 256 out of 10,000, you reduce the computation to be much smaller, okay? And so, but if you do this kind of over and over again, hopefully that you still would get some result, okay, which is good enough. And so this is what we call the stochastic gradient descent, or SGD. The stochastic means that you are randomly choosing 256 or 32 or 64 out of the complete data set, which could be 10,000, could be 1 million. And by doing this in a random way, often enough, hopefully your final result will be as good as you use the complete data set every time. Okay, so this is the SGD, okay? And so the other decision is that once you know your weighted gradient, you know that which way you're supposed to go, how big a step you take, okay, using this gradient is another decision. And that decision is going to be what we call as learning rate. Do you use 0.1, just say, oh, I know that I'm supposed to move this way, but I'm not going to take a big step, but I take 0.1, just change my position a little bit, okay? And by changing that a little bit, okay, and you will be not making a big risk. Or in some cases, if you make a big change, then your search, you might go back and forth because, for example, when you are in a certain terrain, okay, you'll be starting from some high position, and if you take a big step, you may be moved to another position which is too far away from this. But if you take smaller step, hopefully you will gradually come down and eventually you will be able to reach it. But if you take a big step just because you are here, then you may overshoot and then you are going to be in some, position and you have to come back, and so they will be not so desirable. So learning rate is also a parameter that we can adjust. Okay, just like the when we say stochastic gradient descent, that how much is the mini batch every time we should use 256, 64, or 32 or something. Those are the different possible parameters that you can say, this time I'm going to use 256, this time I'm going to use 64. And for the learning rate, you can start with 0.1 to say every time when you compute, after you have computed the gradient, then I'm just going to take 0.1 of that gradient, okay, into my update of the parameters. Okay. So later we'll be looking at the program, and I will show you this particular program. Let me see the edges. Okay, I will show you, this is the homework, but I will show you another example program. In this example program, you can see that it actually has put all of this, the learning rate, the epoch, okay, the batch size is the mini batch, okay, how many you want to use. All of these are the different parameters, okay, and you can define that to be a whole set of hyperparameters that you can choose to use when you are doing the training. And so you can make that to be separate from your own program and just put it in some place. So next time when you come here, all you need to do is to say, okay, last time I update, I used my training to do some certain way, and all I have to do is to update this. My learning rate, okay, it was, this is 1e minus 2 means 0.001. I can update this to be 0.00, another 0, okay, which means LE minus 4 or LE minus 5. And batch size, I can simply update here to say, oh, this is 64 right now. I'm going to change to 128 or something. So all these hyperparameters can be adjusted, okay, when you are doing it, and every time when you use different hyperparameters, a little bit different result, okay. But in unfortunately for now, we do have a lot of decisions are very experimental. Okay, we don't have precise science to say that you should always do it this way. Okay, it will be depending on your just kind of try and error, or maybe from your experience, or maybe certain data set has certain property, so it might be better for you to be using bigger or smaller learning rate, or bigger or smaller mini batch, and this and that. Okay, in in the future, when you want to take our course that we have another course which is going to be talking about deep learning specifically, they will be looking at much more detail in terms of what are the different strategies that you can use to try to pick the hyperparameters, pick the architectures, and pick these all different things. But we are not going to go into the detail in our discussion in this class. Okay. We have also introduced the neural networks, and the neural networks is to try to expand the simple model of having just one W, and which is going to be operated on the input data, training data set, into if you have two such W. Okay, if you have two such W, then you can think of that to be you have two layers of the neural network. So given an input data X, then you will be able to go through the first W, the W1. Okay, this W1 here is a whole big matrix. It's not just one parameter inside of the matrix W. Okay, so this is the first big matrix, or you can think of this to be the first layer of the system. And then you produce the kind of either the prediction or the process output from the first layer, okay? Then usually we'll put some activation functions after that output to try to filter out or try to make some early decisions according to the first layer result. So here you can see we have a max of 0 and this is the very commonly used the ReLU. Whenever your output here is 0, then I don't take any value at all. But if your output is greater than 0, then I'll give the whole thing to the next layer. Okay, so this is a ReLU function that we can use. So this we also use the name to say that you can put a activation function after the first layer, and then after that, then you will be able to feed that into the second layer. Okay, and so again, that if we look at the program architecture, okay, so here you can see that we have the layers. Okay, so each layer you can see that we have in here the example. We will have the convolution operations, okay, which is just like our W. And after that, usually we'll apply some activation, and ReLU is one of the activations to try to filter out some undesirable result or try to help the system make some early decisions. Okay, so this is a ReLU. And after that, then today we'll also talk about, then usually we will apply another operation, which is going to be pooling. Pooling is try to reduce the information because your information originally could be a very big picture, and we can try to, after we have learned something about it, then we can try to reduce the size even more, okay, to make it to be smaller piece of information before we feed that into the next layer. So every layer, usually you would have some convolution operation. For the machine learning, you have some convolution, you have the activation, and you have pooling. Okay, and this is something that we also want to talk about today. Okay, so suppose that you have a two-layer network like this. Okay, two metric or two models that you want to their individual set, individual WI, which is going to be your individual domain dimensions. Okay. The reason why we want to have the ReLU function or activation is so that it can have the capability to help us transform from some input kind of dimensions into another dimensions. So here, for example, suppose we have input data sets which would have all these red dots. We want to separate from the blue dots. If you just have this, it's almost impossible for you to try to find a linear model to separate the two. But once we use the activation, we can try to compute its say, for example, like a radius, okay, and as well as its angles. Then we can try to map that into another different dimension, and that would allow us to be able to look at them to say, oh, these are the size of the radius. So how close are they to the center of the data sets? Okay, and then also we have the another set, which is going to be those blue dots, which they are more farther away from the center of the things. Yeah, we'll also touch about some of this activation function later on with some more examples. Okay, so after we have these layers, sometimes that we can have the layers to be convolution, just like what we have for the computer vision, but we also can have fully connected networks, okay, which is in the later on trying to help us to make some final outputs, okay, by putting all informations into consideration and to be able to try to produce the final prediction, okay. So after we have this model that you have the W1 and W2, then you can definitely imagine that, okay, to add an extra layer, to have 3 layers, mathematically, they are kind of conceptually they are the same. You just keep adding extra W, okay? And the decision to have some extra layer or not, again, is not something that we can scientifically prove. Adding extra layer is going to be better, but sometimes actually it's going to be by experience. And later we'll look at the, when we talk about more about the computer vision, then we will see that there are different projects which has been conducted. Some of them, they are not using so many layers. Some of them, they are using many, many different layers. And using more layers doesn't always give you a better result. Okay, and given using more layers, actually, it's going to consume more computation power because that each layer needs some processing, and that processing will be consuming your computing power. Okay, so in any case, a neural network can be modeled in this way that we can have some input, and the input could be your specific, for example, your input data could be 28 by 28, and then with 3 colors, and you have a total of total of 3 data size is 72 numbers, and then when you go through each of this W, the W here can help you to produce something which then will feed them into the middle layers. And the middle layers, usually we call them to be the hidden layers. The hidden layers means that from the outside user's point of view, they don't see the intermediate layer. They will see only you give it the input and you get some output, okay? So again, coming back to our program here, you can see that we have this program structure. We're going to be defining layer 1, we're going to be defining layer 2, okay? But eventually, when we try to produce something, you can see that we will take the X and we simply feed the X into layer 1, into layer 2, and you do this and that, okay? And eventually we'll return the result, which is the X, which is the output. So from a user's point of view, okay, user means that, when after you have trained a model, then whoever want to use your model to train some data set, they will simply say, oh, I'm going to give the data set to your model, but I want to get some result, which is going to be output. Okay, so the inside your neural network, how many layers you have, it's not really the user's concern. The user could, your model here could have 1 layer, could have 2 layers, could have 3 layers. The intermediate layers in between are invisible to whoever is just using your model. That's why we call them to be hidden layers. They are inside. And how many hidden layers you have, they may not know, and they don't need to know, okay? But they just need to know, oh, I'm going to try to put my data into your system, so I need to know that your system, what kind of data are you going to take? So here we said that the first layer is going to take it 28 by 28. So before you feed the data into your this model, you need to make sure that your data actually is a 28 by 28 picture. If a bigger picture, process it so that you will be 28 by 28. Okay. How about the output? Well, depending on your job. Okay, if you're trying to predict that, to say that like in our homework, we want to predict a picture is one of the 10 causes, then the output layer here should be one of the 10 possible values, or it can give you 10 different values, okay, depending on what kind of output you. It could be that you have only one of them to be out of the 10 value, only one of them to have the result of 1, the rest of them to be 0, or you can have 10 different scores, okay? And then your output here will be 10 different scores, and you are supposed to make a decision out of the 10 score, which one the particular object is producing the output. Okay. You can see that we can have a 2-layer model, which is taking some input, it will go through the input layer, and then this intermediate layer, you have the final result. Okay. We usually have this activation function, okay? And this activation function is to help us so that we can create more capabilities, or sometimes we say that this actually some memories, okay? So that we'll be able to understand the intermediate output, okay, and put some knowledge in the system, okay? Because if we don't have this nonlinear or the activation operations there, then even when you have more layer from W1 to W2, if you don't have something in between, then the W1 and W2 actually can be combined to have a bigger matrix, because W2 and W1, they both are matrices. We can just multiply them together, and really that you can just have one layer rather than all these different layers. So usually we want to have something in between, okay, to be kind of making some intelligent decisions after you have some initial result, okay? Then you say, well, anything which is less than 0 in the ReLU here, then that result means that the information from the previous layer already decide that the information from that part of the network is not useful at all. So don't produce anything. So each of these activation function actually is not just processing data, but actually is already making some decisions. And making that decision can be, you can have different ways. The ReLU is to help us to say, I'm going to filter out the value which is less than 0. Anything which is less than 0, throw it away. Okay, but anything which is greater than 0, keep it and pass it along. Okay, but you can also use a sigmoid. Sigmoid is to say that, well, it's a similar to ReLU, but the output is not always given out just like it is original output of X value. But whenever you have a value which is greater than something than 0, okay, then I'm going to convert it into 1. So your output, rather than 0 or everything else, it will be just 0 or 1. Okay, so it's just like it's helping you to be making a binary decision to say, I'm going to make a decision when I receive some signal, okay, from some other neuron. That signal is going to be healthy or not healthy, the binary decision. So if the decision is to say, okay, this is greater than something, then this is something okay, then don't worry about it. But if this is something which is, kind of has some big value or something which is important, then you pass the signal along to say, okay, something wrong is happening, somebody needs to take care of it. Okay, so there will be the signal. You can have the output to be 1 and -1, okay, and this is called the tangent activation function. So comparing to 1 and 0, you will be given out 1 and -1. And so depending on your following network, whether it wants to consider -1 to be something that definitely has to take some action because it's a dangerous signal, or just 0, just say ignore it. So either you can say, I want to take something or ignore it, okay, or take something is a positive or negative, okay, and take something to be its original value or ignore the value which is too small, okay. Most of the time we use ReLU, but there are also some modification of ReLU. The leaky ReLU here is to say that, well, if the value is less than 0, don't just suppress it, don't just ignore it, but still give some indication how big is the negative part. Okay, so we can use this leaky ReLU here to say that if the value is less than 0, then we take this 0.1. Okay, so if the value is negative, then we still try to make it to have some value, but reduce the strength. Okay, or you can have the max out. And the max out here is that you can see the curve is similar to this sigmoid. It's not a sharp curve, but it still will have some effect. But this reduction of the value is going to be an e to the power of x rather than the x itself. Here we're taking the x value itself, but here is taking the exponential value of that. So therefore, the value become to be non-zero, but very, very small. Okay, so all these are different kind of activation function you could use, okay? And for some people in some special application, they may try different activation function, but in general, ReLU is the one that is used most often. So if you go to look at the program, most of the time you're going to see that people put some operations, could be convolution, could be some fully connection or something, and after that they put a ReLU, okay, to let each layer to be able to make some decisions, okay, and to have some intelligence in there, okay. Okay, so neural network, okay, you have the input layer, you have many different hidden layers, and you have output layers, okay, and all of this are connected, okay. So when we try to, after we build the neural network, okay, we are supposed to have each of this link here from the input to the hidden layer, and each of this link will have certain weight, okay? And those weights will be captured by your W. So your W1 will be capturing all the weights in here from 3 neurons to 4 neurons. So therefore, this will be a 3x4 matrix. This one here will be a 4x4 because of hidden 2 different layers. Actually, they are 4x4. So therefore, this second W here will be 4x4. And last one here will be 4 to 1, 4x1. So therefore, you will have only 4 weights. And you can see that in here that we have W1, W2, W3. And after you have trained the network, you have the W1, W2, W3. Then whenever you have some input data, then you just feed the input data into the input layer, and then you go through this using the weights which have been trained, which have been produced, then you can produce the output. Okay, so that is after you are trained. But but of course that we want to build the training mechanism. So using that particular example, the 3-layer network, your program could look like this. First, you define that, I'm sorry, this actually is a two-layer network, okay? You can define your program to say, oh, okay, I'm going to define something which is going to have 2 layers. So therefore, I have W1 and W2. And W1 and W2, initially, I don't know what kind of value you should have. So I just randomize it, okay? But I need to know, I need to let the system know what kind of input I'm going to get, okay? So I'm going to have an X here, and X is defined to be what is going to be how many different type of values you can have, and also what is going to be the size of the input, how many numbers or how many, kind of dimensions that your input could have, okay? And so you can define here, say, for example, if we have the N here is the total is 64. Okay, I have 1000 for the D int, and I have the height here to be 100, and my D out is going to be 10. So my output is going to be 10. But my input data size is going to be 1000. Okay, and then I want to have 64. Then I can define my W1 to be taken from the 1000 pieces of information from the input, okay, and then produce feed that into the hidden layer. The hidden layer here is defined to have 100. So you will be the first W is going to be going from 1000 into 100. And then the next one is going to be from 100 to the output, which is going to be 10. Okay, and we will have this N here to tell us to say that I'm going to be using how many different, sometimes we use the idea of channels or how many, pieces of the size of the information, okay? And so once we have defined all of this, then we can set up our system to say that, okay, given us any of this input, okay, for this means P equal to range 2000 means I'm going to do this 2000 times, okay. But even I'm just going to try to use some kind of function, okay, and then try to produce the, you can see from the x, okay, which is your input value, one specific input value, times the W1, okay, which is going through the first layer, okay, and then you had this one here, which is trying to produce an edge, okay, but you can see we are not taking the output from the x.w1 directly to the edge, but we are using an activation, okay. This activation here is, oops, sorry, 1 over 1 plus np times exp of this, okay. This one actually is a sigmoid, okay. So it is actually using a sigmoid for activation. So from the X going through W1, going through the activation, you feed into edge. Then from edge, we use the W2 to produce the output, okay? From the output here, it doesn't do the activation anymore. It just simply take the output directly and say, this is going to be our prediction, okay? So from the X, you will go through this, go into the second layer, and the second layer will produce a prediction. This is going to be Y predicted, okay? So from the Y predicted, then our Y here from the training data, it knows that what it is supposed to be, okay, the labels. So from the X, and we already have the, what is the correct Y. And then from your model, you have the predicted output, and you just try to say, okay, now I'm going to compute the loss to see how your prediction is different from the correct output, okay? And if you do the square of this, and then this is the loss function is defined, you will produce loss value. So you will be able to say, okay, for this current X, what is going to be your loss, okay? And then you just say, okay, this is the first time I get it, okay, and this is the loss. Once you have this result and you know what is the loss, then we can here use the gradient, okay, to compute to see that how much you should change into the W2, how much you should change in the W1, okay, to compute each of this gradient here. And then once you know the gradient, then you can use the learning rate here to multiply into the gradient and use that to update all the values of the W1 and W2, okay. So this is a complete architecture for us to be taking some input, okay, knowing that what is supposed to be the correct output, okay, and then we randomize with initially randomly produce some initial W1 and W2, and then we can try to run that W1 and W2 to produce the output, calculate the loss. Then using the loss, we will be able to calculate the gradient. Using the gradient, then we actually update the W. Then we just keep doing this for many, many times. Here it says T is equal to range of to the 2000, means that we're going to run this training for 2000 times. And hopefully when we're doing this after 2000 times, next time when you have some input data using the same, the weights which is produced, you will get some very good result. Okay, so we can implement this idea using the neural network. Okay, the neural to try to simulate the human neurons, and so we can simply define our neural network with all of these mathematical definitions. Okay, but we will put that into the neural network. Okay. We'll have to try to calculate what is the gradient, okay? And we can define the loss function to be, certain way. The loss function here could be just the data loss, plus we have 2W, so therefore we can take some regularization of the W, and we're going to add them together to give us the total loss, okay? So from the total loss, we can try to say, okay, now how am I going to try to update the W1 and W2, okay? And you can see that this mathematically become to be something which is quite tedious, because there will be a lot of this calculation. When you have a big W1 and you have a big W2, or when you have many W1 and W2 and W3 and such, okay, you can try to calculate using pure mathematical, if you know what's going on here, but that is going to be very difficult for us to try to say every time if you want to change the model, then you need to redo this. When building the neural network, okay, one idea has been proposed, and it has proven to be quite successful, is to say, well, we can try to rewrite or reimagine the neural network way of processing to be like a computational graph. Okay, so in a computational graph, we have the input X with a W, and then we can feed those into some kind of a neuron, okay, or some kind of operator, and that operator is supposed to be able to perform the multiplication operation. Okay, so this one here is going to be feeding those two input, perform the multiplication, okay, and the dot multiplication, then you come up with some score, okay? Then you can take the score, going through some activation, you produce some result, okay? And then I'm sorry, not the activation. Here we're going to try to compare the score with whatever is supposed to be your loss function, okay? Then you produce what is going to be the data loss. Then we take the W and feed it into some regularization term, which would evaluate us to be what is going to be the regularization term of the loss. And then we add these two loss together to produce the final loss, okay? So if we model our mathematics in this way, then we can come up with the idea of the computational graph. So when you have some input data, you simply can imagine you feed this into your computational graph, and this is actually going to be actual implementations of your operations, and this actually can be one giant program, okay, just like in our program here that we have converted into layer 1 and layer 2 and such, okay, so you will be going through once computational graph. Into the convert that into a computational graph, then it's very easy for us to put this into the system, and the system will tell us what is the loss, okay? And the idea of the computational graph actually can be expanded to implement the whole network. So here is an example of the AlexNet, which is one of the well-known neural network. Okay, so from some input, you can imagine this to be a matrix of data fed into first matrix, produce something, and then you produce the second. So you have all of these different metrics, or they are in specific ways. Running through all of that, and eventually running through the last few layers to the fully connected, then you will be producing the loss, okay? All of this are actually operators, okay? And these operators, the user doesn't need to write the program themselves. They just call the system to say, I want to use this operator, I want to use that operator. You just need to define how big each of these metrics is supposed to be. Just like in our program here, we define each of these layers, okay, W1 and W2 here, okay, to be saying that I define this to be certain size, okay, it's going to be the size of 32, this is going to be the size of 64, what's going to be the input and what is going to be output. You simply define that, then the system can put it together for you. And so when you want to run it, you just give it an X, and then it will be calling each of this operator, and each of this operator will simply, be run just like a library function, and you will be able to get the output, okay? Using this architecture, you can build deeper and deeper networks, okay? It's adding more layers in your particular model. It's no more than just adding another line here to say, I want to have layer 3, I want to have layer 4, I want to have this and that. Each of this layer here, you can specify specific operators that you want to use. Here we use the convolutional, we use ReLU, you can use Maxpool, but all of that are built-in functions, built-in operators. So it's going to be quite easy for us to keep coming up with more complex neural networks, okay? But whenever you have deep network, okay, eventually we still need to come back to the question, how are we going to be able to compute the gradient? Because eventually, after we produce the loss function, the purpose is for us to use the current loss value so that we know how to use that to help us try to perform the optimization, or try to go back to update the specific weight values in each of the metrics. Okay, so when you have many different layers, okay, how do we actually try to compute the gradient for each of the layers? That is something using mathematics itself is going to be quite difficult to do. Okay, and so that is when the neural network design, especially the deep neural network, okay, come up with the idea of backpropagation. Given as a computational graph, okay, how do we use backpropagation to help us to be able to update our models? Okay, let's take a break, and in the next class we'll look deeper into the details of this backpropagation. Some computation as a computational graph. Okay, like here we have a computation which is x plus y times z. Okay, this is the result of that times z. And we can simply write, draw a computational graph like this. So you can see we have two operators. One is plus, addition. The other one is division. So you have the x and y. Feed the two into the plus operator. The output will be fed into the operator, which is the multiplication. Okay, so suppose that we have some input data. X is -2, y 5, z -4. Okay, and then you can see that feed this into this. Okay, and this will be forwarded into this. The final result will be -12. With a computer, it's going to be quite easy for us to implement this. We just need to implement the operator of this. It's going to be a function. Take these two parameters, output, take these two inputs into the function multiplication, okay, or the operator multiplication will have the result. The question is that we know that, okay, this is going to be a multiplication, this is going to be an addition, okay, and we want to compute how each of these x, y, and z would affect the result f. Whenever we make some changes to value of x, how is that going to affect our result? We change some value on y, how is that going to affect our result f? Okay. In terms of mathematically, we're going to be trying to compute the differential derivative. Okay, partial derivative. Okay, so that will be just like you're doing this computation here. If you have multiplication, then you will be the partial differential is going to be like this. It's going to be changes here. You have direct result into the output, so therefore it's going to be 1. Whenever you change 1 here, there's going to be another 1 here. If you reduce 1 here, it's going to be reduced 1 here. But if you have multiplication, the two of them will be multiplied. So therefore, if you change one value of z, okay, then the result will be this f here will be multiplied by 3. So you can see the relationship between f and z is going to be depending on the value of q, current value of q. Okay, so it's going to be 3. So in this specific case, okay, when we compute the partial differentiation of x, y, z according to their effect into the f, it's going to be something that just like we're trying to say, oh, what is going to be f in terms of f? Okay, f's change, going to change f, it will be direct, so therefore it will be 1. But when we want to change to see that how z's value, okay, will affect f, or f value is affected by z, we have to do this one. And this one here, you can see from this definition here, we're trying to do the f over Z probability differential of this, okay, then this is going to be equal to Q. And Q right now here is going to be 3. So therefore, we know that this particular value here should be equal to 3. Okay, so mathematically, here we have this equation. But in order for us to try to calculate the gradient, we cannot do it without the actual value of x, y, and z. We need to have the specific of x, y, and z so that we know that Q will be 3, and that will define to say that how z will affect f. Okay, so this particular value 3 cannot be derived directly from the equation, but you have to be derived from the actual execution. Only after you have the execution, you know this is 3. Then you can find out this value here actually is going to be 3. Okay, so in terms of when we have multiple layers of the neural network, okay, it's just like that. You will have to try to calculate each of this one here. Say, for example, F and Q. The relationship between F and Q is going to be whatever you change the value of, depending on what the current value is. And so therefore, it's going to be -4 because right now it's -4. Okay, whatever the change 1 here is going to be multiplied with -4. So therefore, its gradient is actually it's going to be -4. Okay, the same thing. Now, from Q to X, we know that it's supposed to be 1. Okay, whatever change in the X here is going to have direct effect of the value of Q. But how about from X to F? From X to F, you would have to say, okay, X value will change Q and Q's value will change F. So therefore, we'll have to have different layers. You will be value change to Q, value change to F. So therefore, Y value change to Q and Q value to F. Okay, so the result of Y's value, how value will be equal to first layer and second layer and multiply together. And this is called the chain rule. Okay, so whenever we have a computational graph, the computational graph, whenever we want to calculate what is the partial differential W F over Y, okay, it's going to be, we have to go through each individual operators and see how they are going to be accumulating or multiplying all the local gradients together in order for us to have that final. So in this particular case, okay, we know that from F to Q, okay, it's affected by this value -4. But from Q to Y, we already know that this is going to be 1. And so from Q to Y, this one here is going to be affected by any other current value, but it's going to be multiplied by 1. So therefore, this one here under the Y is going to be -4 times 1 because this is a step. X is going to be 4 here and multiply 1 because the operator is 1. So therefore, it's going to have this. Okay, so that is what we call as a big propagation because you can calculate the output from a computational graph. But once you have a computational graph, whenever you want to know how each of the input value would affect the output, we need to do the back propagation of their, kind of a local gradients. Okay, propagate that to the next variable and the next variable. Some of the calculation from this label to next label will have to be depending on what is going to be the current value of the previous of the other side of the operator. Okay, so we can implement this again in the computer program, okay, very easily with a forward propagation, just like we have seen in our program. We can simply just add another layer, and put in this here and this here and this here, and then it will be able to give us what is going to be the final result. Okay, but the other thing which is important is that we don't just want to get the final result, but we want to know the gradient so that we'll be able to use that to update our weights. Okay, So in the most of the program in this particular one, you're going to see that you have this. If you look at this particular structure here, you can see that first you will have performed this model to get the output. Then you use this criteria here to say output with a label, you compute what is the loss, okay? And after that, okay, then you will use this loss here to call the backward, okay? Because from the backward, then we can find out what is the gradient. And from the gradient, we can use it to do the optimization to decide how much of the step you want to take from the gradient, okay? In the between, there is a term here called optimizer.zero gradient. What does it mean? Every time when you try to compute, okay, because every time the result of the gradient, of the value of the gradient will be depending on your current intermediate value. So you need to zero it out, okay, so that before you actually do this one here, because every time when you have a new input, you're going to have a different result of this gradient. So you need to reinitialize it so that you forget what you have from the last input. You can have a set of gradient. For a new input, you want to forget it and do it again to find out what is the current new gradient. Okay, that is very important. Whenever before you do the back propagation, before you do the optimization, you need to try to clean out your previous result, because your gradient computation is going to be based on your last known value for each of the dimensions. If you don't do that, it's going to repeat using the same thing, and your result will be different. Okay, so back propagation is, kind of graphically, is simply say, oh, I have the each operator, which is an f. I have some input x. I have some inputs on y. Okay, so I can calculate what is the local gradient. What is the relationship between x and f, y and f? Okay, and I'm sorry, x to z and y to z, because this f here is supposed to produce the output of z. Okay, and we can define that based on the particular operations you're performing here. If this is add, then we know that this is going to be always equal to 1. But if this one is a multiply, then the value of this, okay, the partial differential of z over x is going to be depending on what is the current value of y when you perform the last time, okay? And so we can define this to be local gradient, and this local gradient for each particular operator is mathematically, we know that, okay? Or you can say that whenever some system give you some particular operator, it knows already how to compute the local gradient. So here again, you can see that when we define the model itself, okay, we are defining our layer 1, okay, and we say that we're layer 1, the first operator we're going to be NN, which is the package. Inside it has the comp2d. So comp2d is a specific function, okay? When we use this one here, how to compute local gradient is already defined. So you don't need to do it yourself. You tell the system, say, I'm going to be having this particular operator in my computational graph. Then whenever you are trying to do the back, okay, you don't have to do anything yourself, because the system already know for each of the comp2d, okay, when you have the gradient kind of backward from the result into the input, it knows how to compute that. And so this particular operation now, you can see in this program, is just one line. But actually behind it, each of the operators you use in each layer, okay, this has to be known. Somebody needs to define how to compute the back gradient from that, okay? But since you're using the system, the operations from the system, you don't need to rewrite it yourself. In some other programs, if you are using your own particular computational graph, then you need to define how to do the backward. So sometimes, if you look at some of the program, when they define the model, then they have the initialize the init function here to define the specific architecture. Then they define the forward to say how to compute each of that. And then they also will define backward. They will define the backward themselves, okay? Because there might be some way for them to be computing the backward propagation in a special way. And so you can do that yourself. But if you are using the standard operations from the library, then you don't need to define the backward yourself. Okay, the system will provide that automatically already. Okay, I'm talking about the PyTorch. Okay, so basically, whenever you define computational graph using PyTorch or some of the framework, it's very easy for you just simply to say, oh, I'm going to be using them specific F here, okay? And so therefore you don't need to write this yourself. Whenever you call the backward, the system will compute whatever is the gradient known so far to Z, and then we'll be able to simply pass it down to X to be, oh, okay, this is going to be simply from the upstream gradient, I'm going to multiply into local gradient to be the downstream gradient, okay? And so no matter how many operators you have, like here, this is a special example of trying to do the, you can see that this is a sigmoid, okay? But inside the sigmoid here, we have W0 times X0, W1 times Z1, W and W2, so this is actually already one layers of the linear classifier, okay? So you will be simply taking, you can see that if we have a function like this, okay, you will be trying to produce almost like one layer of the neural network, okay? And it is taking W0 times X0, W1 times X1, okay? And multiply that, then the two will be added together, and then you'll be added into another W2. The whole thing would then go through this equation here, which is a sigmoid, okay, in order for us to produce the output. Okay, all these operators, you can see each of this is going to be like here, you do the times -1, okay, which is going to be this term, and then you fed into the exponential function, it's going to be this term, and then the result of that is going to be add 1, okay, after that, it's going to simply inverse it to be 1 over x, and that is this whole thing here. So once we can define this computational graph, okay, then we can feed it some specific value of our current W value, current X0 value, current X1 value, then you'll be able to compute forward pass what is going to be the final result. And the final result from this equation here, which is from this computational graph, is 0.73. Okay, forward pass. Now, we want to compute the backward propagation to try to compute the gradient. Then we will be able to say, okay, in the first one here, it's actually not going to be anything different. Okay, this is defining the project differential for each of these operators. Okay, we know each of this equation. Then we can simply say, okay, the first layer, you're not really doing anything. So therefore, the first one is going to be by itself is 1. But when we try to convert, propagate this one through the 1 over x, the equation for that is this. So we will take this value and then compute that. Okay, 1 minus 1 over x squared. X squared here is going to be 1 squared. So therefore, this is going to be this. Okay, so it's actually going to be this 1 over x here is going to be minus 1 over x2. Okay, and it's going to be all into 1. And so therefore, it's going to be, because, I'm sorry, the x value passed into this one here is 1.37. So 1.37 is going to be this x. Okay, so we're going to do -1 x squared here. And so from the upstream gradient is 1, but when you pass through this one here, the local gradient is going to be this value here. And so therefore the output gradient, the downstream gradient is going to be 0.53. Next one is going to be +1. And the +1 function, we know that it's not going to change anything. So therefore the next one is going to be just 10. Okay, it's going to be this one multiplied by 0. It's a little bit interesting because that the differential of that is going to be, again, taking the e of x, and then here this is the last value, and this one is going to be multiplying into e of -1, okay? And so therefore it's going to be e of -1, okay? E to the power of -1 multiply into this one, e of -1, okay, multiply into this one is going to get the result 0.2, okay? So that's going to be the local gradient multiply into the upper string gradient, and this is going to pass down to the next one. The next one here is going to be multiplied with the -1. So therefore, we're going to take this -1 here, or the a value, okay, and that is going to be times -1. And then we pass down this to the lowest one, W2, from here, okay, into this. But this is a +1, so therefore the plus operation, so therefore nothing is going to change because the plus means that it's going to be the same. From that, okay, whenever we want to do this 0 here, and this is a multiplication, so therefore this 0.2 is going to be affected. What is the current value of the W, okay? And so therefore the x0 is going to be 0.2 multiply into 2, and so therefore this is going to be 0.4. But the upstream here is going to be 0.20, -0.2, because this one is going to be multiplied into what is the current value of x0, which is -1. So backpropagation will allow us to be using the whole architecture or the flow, okay, of the operators, and also what is the current value used in computing the forward path. And then from that, we'll be able to calculate what is going to be the gradient in the backpropagation, okay? Inside with the sigmoid function here, but in terms of the backpropagation, it doesn't get okay. We can also say, oh, this one here, I know the formula is this, and so therefore I'm not going to do the detail. I can just apply this one with that one, and then compute this value into this to be the 0.2. You can do it the detailed way, or you can do it the big way. Is the same. So here I'm doing the sigmoid for the activation, and here in the program we are doing the ReLU for the activation. So the ReLU, you will have its own way of calculating the backpropagation. So you will not be doing the detail, but you will just say, oh, this whole thing here, I'm going to take whatever is the result from the upstream, and then going through the ReLU's kind of a backpropagation rule, okay, and you will pass down the gradient to that way, okay. So specific patterns in some gradient flow, you can have the addition, okay? Then the gradient will simply distribute it without any change. You can also have multiplication. Then you'll be depending on the current gradient from the upstream with also the value of the other side become to be the local gradient, multiply into the local gradient. And so therefore that will be becoming, there will be kind of a swap of the values to compute the multiplications backpropagation. If you have something which is copied from one value and you copy into another, then the gradient is going to be added together when you go in downstream. Okay, because whatever change you make here will be coming to be the change in here as well as the change in here. So the result is kind of amplified by how many ever copies you make. So when you compute the gradient, all of them needs to be accumulated together to become to be the downstream gradient. When you have the max, okay, which is like our activation for the max, then you'll be depending on which value is bigger. If you're doing the max and last value here is 5 and this value is 4, then the local gradient here will be changed to 0 because this one here doesn't take into the calculation of the next one, okay? But this one here, whatever is the value in here, okay, you will need to be taking the whole thing into one way. So the max will be choosing one of the branches, one of the inputs, okay, to receive the whole gradient. Okay, so if we have a computational graph like this in the forward pass, which is 4 lines, S0, S1, S2, S3, and then I have the output, okay? So it will be 5 lines. But in terms of calculation backward, then you will be doing this to say, I'm going to be calculating the gradient of this into that, and sometimes I take it, sometimes I have to multiply with whatever is the last value of X. So if you write a computational graph yourself using the simple operators, okay, and you do that as a forward pass, then you can design your own backward pass, okay? And then your backward pass program will have to be calculated individually in this way. And you can see that in this calculation here, I need to have what is the X1 value, what is the W1 value, what is the X0 value, what is the W0. I also need to have this S2, S3, S, you know, and such, okay? So all this S values calculating S0, S1, S2, S3, okay? When we are running the training, they need to be saved. They need to be saved, okay, when we're doing the forward pass. Okay, so that's why that whenever we are trying to do the training, okay, in some program, you would have the specific operation to say that I'm going to be doing the training, okay, and sometimes they would separate them to say that I'm not doing the training, okay, so I don't need to do the in this particular program it doesn't have. If you look at some of our, this is a program example I was going to talk about in the next lecture. Then you can see that in the program, let's see, there's a forward model. Okay, this is a training loop, okay? But when you're doing the evaluation, okay, then they have this extra line here to say with PyTorch dot no gradient, okay? Because when we are doing the evaluation, we are not going to be doing the optimization anymore. So we are not going to do any backward propagation. So therefore, we don't need to compute the gradient. And so therefore, we don't need to save those intermediate values in order for us to compute it. So with this extra line there, that means that you don't need to save them. So therefore, you will be faster and also it will take less computer memory. Those intermediate values are necessary for us to stay. Okay, we will be able to just use the W1, W0, and W2. These are the model weights that we can compute the prediction. But if we're going to be doing the backward propagation, then we need to save all of these values. Okay. So trying to produce the prediction is much easier than if you're trying to train the program. When you try to train the model, then you need to save all those intermediate values, and you need to go through all these different steps of calculating the gradient in the program. Okay, here you can see that there are only 5 lines here, but here is like 10 lines. And when you have even more complicated computational graph, then the backward propagation will become to be even more difficult. Okay, so the raise of the graph is just trying to show that you can do this in many different ways. And in PyTorch, there are many already built-in operators or different functions that you can use. Just like we can see that we have the where is, let's see. But in any case, these are some of the operators that we did. The tangent function here, there's probably some redo function or or something in here. So all of this, okay, they are already built in as Python operators. Then how do we perform the backpropagation for all of these standard operators are already defined. So you don't need to write your own. You can just use them, and the system will know exactly how to calculate the backpropagation. Okay, I'm going to skip this part on the vector because that when we are using the computational graph, which is showing the example of one scatter, one value into another and such. But when you have each of that is not x0 is not just one value, but it's a vector, the same idea can be used to perform this backpropagation. Okay, so the difference is that the function is a little bit more complicated, okay, but still the calculation, the way of calculation or the way of performing the backpropagation is the same idea. Okay, so that is the discussion on the backpropagation, okay, and I'm now going to move on to the next topic, because after all, what we are trying to do is not just neural network. In the first part of discussion, we are actually doing the computer vision. We're going to be looking at the pictures. And when we are trying to look at the pictures, the most useful techniques right now is convolutional neural network. Okay, convolutional neural network is designed specifically to try to perform the operations for computer pictures. Okay, so I'm going to skip the first few slides because that's what we have just discussed. Okay, so now let's look at picture. So again, if our input is a picture, okay, we need to somehow let the system understand this picture, okay, in terms of its numerical values. And the picture for us human beings, we don't look at that to be bits. We look at that to be pixels, of course, but we are actually not just using a sequence of numbers, right? We look at that to be somehow with the concept of shape, somehow with the concept of darkness, somehow with the concept of this texture, and we also have some association with, say, for example, this whole thing here, we don't understand to be a triangle, but we understand this to be some kind of a ear. So we have those semantic information in our mind when we try to identify what is a cat and what is a dog, okay? If we're looking at from mathematical or from computational point of view, okay, we can still say, oh, this is a computation trying to take the value of x, multiply into w, and it's going to be able to help us produce the score of classes. And in our first discussion, we simply take the sequence of pixels together, okay, rather than picture. So we have the RGB. So we have 3 sequence of numbers. Each of the number is a pixel value, okay, in R, in red, in green, and in blue. Okay, we just say, okay, this is going to be your W. It's going to be, this is going to be your X, okay? And you're going to multiply that into W, and you're going to get the class score. Or we can try to have some other way to look at it, not just individual pixels. So we can take a picture. So one way to do it is to try to run that into color histogram. Okay, so histogram here is not so much of the specific location, but say in this picture here, how many green we have seen, how many red, how many pink, how many purple, and how many blue. Okay, and we simply try to go through all the pixels and accumulate the total number of some color pixels. Okay, and that will give us also what? A sequence of numbers. Each number is going to be representing the how many times that particular color has appeared. So you can understand the picture not by pixel, but by distribution. that also numerically is meaningful. So for some domain of the input, this is probably better than trying to use individual pixels. Okay, so you can imagine that look at a whole some pictures of some stars. Okay, maybe this will be more meaningful. And so that's why that the people sometimes they use spectrum. Okay, or you can compute what is a histogram of oriented gradient. What is the oriented gradient? For each picture, you divide it into a small area. In each of the small area here, you try to look at the basic shape of that particular inside of that grid. Okay, here you can see that this one here, the shape is like it is going horizontal, so therefore it shows the horizontal. In this one here, you can see there's a slope, so therefore it shows the slope here. Okay, so we can have some orientation gradient of each of this, okay, and then put it together. So then, rather than saying the RGB strength, we can put all of these different kind of angles together. And this will be very meaningful if your input data is more about the shape, okay? And you can have all of this shape together rather than pixels, gray RGB together, okay? And use that to train your system, okay? So you can see that if you use your imagination, you can see a little bit of the graph shape. I'm sorry, frog shape, okay? In this one here, okay? So in any case, when we try to let the machine understand about pictures, okay, we need to convert a picture from some our physical, kind of picture into some sequence of numbers, okay? And the sequence of numbers could be in many different forms. The bigger words, meaning that we can divide them into individual small grid, okay, or small patches, okay? And then each of the patch, then we try to see that what kind of picture is that, okay? Just like trying to do, remember we talk about the nearest neighbor kind of thing. So there could be already some code book, okay, so some basic shape. And then try to match each of this to see that which one are they closest to, okay? And so you can see each of this picture here can say, oh, okay, I have this code 1, code 2, code 3, code 4, and 3 code 2, code 3, code 4. So convert them rather than use RGB, it could be a whole bunch of this code together, either in sequence or in occurrences and such. So each of that, in any case, are converted into a set of numbers, and the set of numbers, then we can try to go through and try to see, understand what's going on, and then train according to those numbers. Whatever you use, whenever you are doing this, okay, you are not really using a picture, you're using the numbers, okay? So one way to do that, okay, in the convolutional neural network is actually to have some operators before our fully connected layer here. We try to convert this something into something we think is meaningful for the computer vision. And what do we mean? Okay, so in the computer vision, okay, there have been many studies, and one of the things people have found, okay, is to use something called sorry, I forgot to share the screen. So therefore, the slide we're going to have will not be in the okay. In the study of the computer vision thing, okay, there's a special operator, okay, which is called convolution, okay, or filters, okay. Let me share with you another slide, okay, which is from our another class, which is the computer vision class by Professor Yang I think he will offer the class in the next semester. Okay, you have the computer vision class. And so for those of you who are interested in the computer vision specifically, you can go to take the class. Okay, so the computer vision area is to study not just machine learning, but actually to try to let computer understand pictures. Okay, and this actually, the field existed even before the machine learning. Okay, so in the past, they have tried to use many mathematical kind of functions, okay, or trying to compute pictures, still in terms of pixels, in terms of this and that, okay, and then try to adjust, okay, the pixels according to its brightness, according to its contrast, and this and that, and also try to come up with different ways of making, you know, the changes to individual pictures so that it will be easier for computer to understand what's going on. Okay, so here, for example, like this is trying to look at different colors, and by differentiate different colors, you can see that the flower, okay, by taking the R and G and B and also using the function of this R and G and B here, I can pretty much see the shape of a flower without regarding the details of the textures. Okay, so you can see that by first taking the R and G and B values and then going through these functions, I will be able to have something which is a little bit more meaningful for computer to try to understand what's going on. Okay, and you can also change the lightness. You can change the different saturation and then this value. By using these techniques, okay, computers will be able to say, for example, suppose that we're trying to ask the robot to grab a phone on a space, on a tabletop. Okay, so I can let the robot arm take an RGB image, then use this grayscale to green, and then project that according to some function to get rid of the noise. Okay, or the shadows, okay, and then after that, I will be able to try to find out the detailed shape, okay, which is different from the rest of the color, to have the segmentation, and then do some post-processing to say, for the segmentation, I'm not interested in the inside individual curves, and come up with this, okay, and you can see then this is roughly the whole shape of cell phone, okay? Then with that particular shape, I can compute where is the center, where is the boundary. Then I can pass this one here to my robot arm. The robot arm will be able to say, okay, given this particular shape and your center and this and that, where should I grab that particular objects? Okay, and that will be one way to be using, this computer vision techniques. So next, we're going to look at in the computer vision or the image processing technology. It has also developed some technology for us to be looking at pictures in terms of the convolution. Okay, and so we'll introduce a different type of convolution, which introduce different filters, and then some of them will be taken into the idea of the machine learning to use the idea of the convolution or the filters to be built in the convolutional neural network. Okay, let's take a break and then we'll come back to look at this. So in the computer vision or image processing study, it has been working on different type of what they call as linear filters. Okay, linear filters is an idea that is still on in terms of the pixels. Okay, each of the computer image. Okay, as we know that we can represent into a pixel, and each of the pixel has certain values. Then it has studied what they call as a linear filter to say I can have, see if the original here is 7 by 7, I can design a filter of certain size. Then each of the filter can be put on the picture as a partial grid, okay, or partial picture, and then multiply each of the value with the value in a specific pixel or cell, okay? And then you will be able to produce one specific value. So by using this particular operation, the original picture, I can take the filter and then put it in each of the area one by one. Then I produce an output new matrix of pixels. And this whole thing can be done using the filter with two different kind of operations. One is a convolution operation, which is a multiply, and the other one is the correlation operation. If you want, you can also do that, just to say that F and H are not really multiplied together, but I'm using a correlative operation to see how are they close to each other or not, okay? So for example, here we have a filter like this, okay? We have a value of 111, okay? And the whole thing, you can see that when I multiply into an original target picture, okay, it will be just like, you know, the whole thing is going to be multiplied by 9. So if you take 1/9, then you will give us a value. So I can use this and then try to look into picture and then try to go through each of the area using this filter, okay? So if you look at this, then you can see that if I have an original picture, which is like this, most of them are 0, dark. Some of them are 90, which is bright, okay? So I take each of this, take the filter and I put it into each 9, cell grid, okay? And then I put the output into the G matrix, okay, which is simply using this particular operation that each of this value is going to be a sum of all of these 9 multiplied together, okay? Then you can see if I do this over and over again, so the original matrix is going to be, okay, you compare this original with the output. What is the result? What is the effect? Don't look at specific number, but just look into the overall general picture. It's actually to capture here, okay, it's actually is a shape of some kind of a square, okay? And you can see that here, even though we have a noise of 90 in the original picture, in the output here, the noise is gone. Here you can see we have this one here. Inside the white area, you have the black area, okay? And this is the noise, but in here, again, that is gone. So from the original picture like this one here, if you use this image filter, think about this idea of filter is actually filtering out the noise or the small pixels. It keeps the general shape, okay? Not as precise as that. On the other hand, that it actually produces something which is just like this. So using that particular one we have just seen, if you have an original picture like this, you're using that particular kind of filter, and you may produce something like this. This one here is not the same as what we have seen. You're using a filter, okay, from the original into the output. That's the effect. So filters are actually, by using different type of picture values, actually can produce a result to be, for example, here, compared with this original with this one. Do you see the difference? There's actually no change because I have this filter has only one out of the 9 cells. So every time when you go through something, you will keep only original center value. The rest of value is not changed, okay? But if I use like this, put in this one on the right-hand side, then every single pixel in here will be shifted to the left, okay? Because I'm taking the original picture, which is one in here, but I said go to the that. Okay, so therefore everything is going to be moving to the on the right hand side here is taking the value to the right, so therefore every picture is going to be moved to that. And if I have this to be a value of 2, okay, in the center value, then you can see this one here actually is supposed to be sharpening. Okay, if you look at this one and this one here, you don't say, oh, this is, you don't see really that this is sharpening. But if you look at the big picture, it's going to be, this is the original picture. And if you use that particular thing, you can see this actually is sharper than that. Okay, it is using this particular filter, which is, well, everything else is 0, but there's a value 2 here. Okay, so you can see that by using different filter, before and after picture actually can make some difference. And if you use a filter like this, 1 2 1 0 0 0, -1, -2, -1, this actually is able to produce a vertical edge of this picture. Okay, what is a vertical edge? So anything in here with a sharp edge, okay, and it is in a vertical way, because this is shown in the vertical way, and strengthened in the middle, okay. I'm sorry, strengthened in the cell here, but deep this 0, okay, is actually able to produce these lines, which are vertical edges of the original picture. Okay, if I change this filter to this way, horizontal, then you can see that it's able to capture in this original picture, not the vertical lines, but now horizontal line. This one here, you can see this is actually the slope line. It's a, kind of this way. So you'll be captured both in terms of vertical as well as horizontal. But the vertical one is much more clear, okay, because the line is more clear, more vertical. But any of the line which is just vertical, the horizontal, it will not be caught. Okay, so using different filters in the image processing technology actually can help you to make the original picture to capture only the important features that you want to see. Okay, you can use it to sharpen, you can use it to capture certain edges, you can use it to be doing many different things, okay, and using different filters, okay, you can also introduce gradient in there, okay, and you can also use the content to say that for each of the pixels, I'm going to not look at just you, but also all the neighboring area. Okay, but when you're doing this, then the picture becomes to be fuzzy, but that also be useful, okay, if you just don't want the detail, but you want to see just the general shape. So this one here would be very useful if you're trying to produce something which is kind of try to hide the privacy of people, okay, because doing this, you won't be able to see the actual face, but you can see the general shape, okay. So taken into this technology, you can see that we can use different type of linear filters. Each of this linear filter would be able to help us catch certain, kind of a specific things that we want to see in the picture. Okay, can catch horizontal edges, can catch the vertical edges, can also use it to sharpen, okay, can also try to, move this and that, okay, and make it, smooth and such. So for machine learning, this actually is very powerful because we can ask machine to say, try different filters, process the original picture, and see whether you can come up with some features. And those features, if they can help us understand what is inside the picture, then we will be able to make better capabilities to try to understand and try to identify, try to classify the images. Okay, so that's the idea behind the the neural network, but now we are expanding the capability from just the multiplication. You know, when we talk about the neural network just now, that we're talking about multiplication, we're talking about addition and such. But now we can use this idea of convolution, which is use a filter and then going through the original picture and then try to use different filters to help us produce different features. Then when you produce different features, then later on we can put them together and then try to understand what's inside of that picture and help us to do the classification. That's the idea behind what we call as CNN, convolutional neural network. Okay, so convolutional neural network, the one of the first ones to produce it is called the LaNet. It was published in a paper in 1998. Okay, started to use this idea of the convolution. Okay, and then later on, there was more powerful convolutional networks, and also with deeper networks. Okay, and then AlexNet is one of the very popular one, published in 2012. So they have done a very good job, okay, to help systems to identify or classify objects inside the picture, okay? And since then, okay, many of the newer network and newer capabilities and newer models has been produced. And you can see that you can do the classification, you can try to retrieve pictures out of the whole bunch of things to say this is something similar to what we have in the original picture. And you can also try to do the detection to identify, oh, this is a human, but where in the picture is a human with a bounding box, okay? Here you can see the picture, there's a dog and also a cat, and the dog and cat, of course, the bounding box is not so precise, but at least that is able to identify with the probability to say that how sure that it is a cat in this area. Here it says 92%, I think, 96, 98%, okay, and you can see each of that, okay, with detection. And then later, the technology has also been expanded to be able to do segmentation for each of the objects, not just, what kind of things, but also the overall shape of that, okay? And I can, from a picture, I will be able to identify that area. And now, of course, that the convolutional neural network is everywhere, used in autonomous driving, and also to be able to do the posture, as well as many different things. You can use that even to try to design some games. And then the capability now also being used in image caption, meaning that when I look at the picture, ask the computer to not to just understand one particular class, but relationship between all these different classes and come up with a title for that. Okay, so here it says that this is a white teddy bear sitting in the grass, and this is something that a woman is holding a cat in her hand. Can you see the cat in her hand? So why is this caption in this way? Because somewhere in here, probably it looks like a cat with a fur, right? And there's a hand, so it's imagining that, somewhere you can see that it's just like a shape of the woman holding a cat. And this one here, a woman standing on a beach holding a surfboard. Can you see that? What is this picture? What do you see? Is it a woman? I don't know whether it's a woman or not, but I think it's a woman. It's upside down. It's holding herself upside down. Okay, the hands here, the face here. But the whole shape here, we consider to be a surfboard. Okay, so it was able to capture the idea that there is a woman, okay, and there's beach, okay, there's a lake, okay. So reasonably, there's a surfboard. So you simply put this together and say, oh, this is the caption: a woman standing on a beach holding a surfboard, which is more reasonable than like, a woman's on a beach, is upside down, okay. And this is more reasonable explanation. A cat sitting in a suitcase on the floor. It's actually not on a suitcase, but actually inside of a suitcase. Okay. But anyway, you can see the idea that, many of these technologies. Okay. So CNN is one of the most powerful technology now being used by machine learning, by many applications. And it has this simple that we already talked about. We'll talk about fully connected layer, we'll talk about activation functions. We will introduce the convolutional layer, okay, and later, we'll talk about the pooling layer and as well as the normalization, okay. All of this, you can see that we can use that to build something like a AlexNet, okay. The CNN, okay, for just one layer already, we can see individually, they can be used to try to detect certain features, a vertical line, horizontal line, a particular shape, or this and that. But with the design of the neural network and deep neural network, then we are able to let the machine learning to be using multiple filters, okay? And in each of the filters, also we can do multiple of them together, one layer after another, and each layer use a different filter, and this different filter can detect different features. So by using you can think one is a parallel, meaning many different features detected in each layer, and in multiple layer, meaning that you can detect a specific feature on top of something and then putting the two together to make more sense. Just like when we look at this, a woman holding a cat, you can see detect a woman, detect something like a cat, and somehow you put them together to say, oh, this is a woman holding a cat. So by using multiple layers, we are able to have multiple features detected and then added together to have this multiplication knowledge, okay? Multiplication of knowledge, okay? So AlexNet was one of the most successful, was able to identify many different objects, okay? It has this one layer here, one layer here, another layer here, another layer here, another layer here. After that, okay, then it has a fully connected here to try to understand all the features detected and then try to make some sense out of it. Then finally use a softmax here to say, I'm going to give you some probability what this is about, okay? So it is able to identify pretty, in terms of the technology at that time, very good score in terms of the identify classification, okay? Later on, there was another work, VGG, and you can see VGG said, well, if you can do it with 3 different or 5 different layers, I can do better, okay, by adding more layers, okay? And by adding more layers, okay, it will take longer, but on the other hand, that hopefully you produce better result. And finally, you have VGG also, as a 19, okay? One good thing about whenever you're using the deep neural network and do the machine training, machine learning, when you do the training, is that you just design the layers. You just say, I want to use this layer, I want to use convolution, and you just specify the size. But you don't need to come up with a filter yourself. Okay, by using different filter, we have seen that they will produce different results, right? But using the machine learning, you simply say, well, here I have a picture, here I have the result, okay? And here I have the correct answer. So why don't you try everything and let me know that what kind of score you can have. If your score is not good enough, just use a bit propagation, go change. How do you change it? The user doesn't need to know. Okay, so that's why that when we are, kind of doing our homework, actually, I'm not asking you to be explaining to me what a T-shirt is different from a boot. We don't really care. Okay, and how a T-shirt is different from number 2. We don't care. In the original image processing technology, you need to care. You need to design the technology to understand these are numbers. What kind of mathematical function make it to be a number? What kind of mathematical function make it to be a T-shirt? But now we are using machine learning. What do you need to do? Show me the picture. Show me the picture, and I fit it into this AlexNet. I fit it into your model. Train. Okay, what do you need to do? Specify the hyperparameters. How many layers do you want? How many different, epoch you want to have? How many, what is going to be your loss function you want to define? Okay, the machine will do the rest of the job. You just do the forward, then backward, forward, backward. You will calculate the loss and this and that, and you will have your final thing. So, continuum network. Okay, it's going to be a fully connected layer. Function. We have already told you. So you don't need to research. We are now going to be talking about convolutional layer, and we can say, okay, to reduce the effort, we can try to downsize it so that it can be pulled together. Okay, and there are some mathematical functions here to make the computation easier. But fully connected layer is all you have to do is to define it. Okay, so originally, okay, when we have the linear classifier, we take the input of the sequence of numbers, 32, 3072, and then we have produced this, we put a model of W, and we ask the machine to train. We give you the answers, okay. In the convolutional layer, okay, we are now not just taking one specific single dimension, but we are going to put it together, okay, and then say, use a filter. The good thing about the filter is that the filter is a two-dimensional thing. So when I look at the one original picture, okay, you will not be looking at each of them horizontally, okay? And you can see that with a two-dimensional feature, you can actually capture many different part of features in the original picture, okay? So you can slide the filter over the image spatially, okay? And then try to capture the information in each of these area here, okay? So if I have a picture which is 32 by 32, and I have certain colors, RGB, then the input information can be modeled 32 by 32 by 3 metrics, okay, or tensors. I design a filter which is 5 by 5 by 3, okay, so each of the image, kind of patches will be handled by 5 by 5. And I can have 3 here, means that it's going to be using 3 different type of filters. So from the same picture, I will use 3 filters to try to capture 3 different things. Just like when we look at the picture, our eyes actually, we see the features together. We see the shape, we see the color, we see the things. We don't really differentiate that, but we tell the computer to say, well, each of them will try to do something different, okay? So by taking each of them, okay, and then, using this 5 by 5 by 3, then I will be able to compute, just like originally we use the linear to compute, come up with a number, okay? Now I can over the whole picture one area at a time, over and over again. And so therefore my output will be something smaller, okay? Because originally I have 32 by 32, right? And I have 5 by 5. So going through the 32 using the 5 by 5, how many times will I have to go through in order for me to reach everything? I have 32, I have a 5. So each time I slide by one, when would I reach the end? When I originally, my right-hand side column will be at position 5, right? Because originally I have the 5 by 5. So it's starting from 1 to 5. So it'll be starting from, when I shift the next time, you'll be in what position? 2 to 6. Next one, 3 to 7. Okay, so eventually you will reach to 32. When you reach 32, what will be the first one of the 5? 32, 31, 30, 29, 28, right? So you will be starting from the first one and eventually you reach 28. When you reach 28, then everything will be covered already. And that's why the output will be 28. Okay, it will be 28 this way, it will be 28 this way. And so therefore the output of this filter using 5 by 5 will be 28 by 28. The 3 filters, okay, can be combined together to have 1. Okay, so the RGB together, okay, will actually come out to be just 1 output. Okay, so that will be our what we call as the activation map. Okay, so I can have 3 different filters. Okay, and so I can produce 1 for this and 1 for this and 1 for this. Okay, so usually in a convolutional neural net, CNN, we would design a convolutional layer. You would have many different filters. How many filters do you want to have? Up to you. Okay, but you need to decide what's going to be the size of your filter. So if you decide your size of filter is 5 by 5, okay, then this 32 by 32 here, if you 5 by 5, you'll begin to be 28 by 28. Okay, originally you have RGB, 3 channels. Okay, we'll call it 3 channels. But you can say, I want to use 6 filters. Then your output will be 6 rather than 3, because RGB actually will be combined together into 1, but you can use 6 filters, so therefore you have 6 output channels. 6 output channels means what? Not color, but 6 different features. Some of them trying to catch a vertical edge, some of them catch the vertical, horizontal edge, some of them try to catch the overall shape, some of them try to catch the darkness or something like that. So each of these 6 activation map here would try to capture something from the original picture. Okay, and this will be considered to be 1 layer because they are all taken from the original picture, produce 6 different output images. Okay, 1 layer. Now, after 1 layer, okay, when we just have our computation, we can also add a bias. So after you do the multiplication, you can add the bias, then you produce this one. Okay. So now, if we have many different pictures, okay, each of them going through this one here, then we have many such output. Each of them still is going to be 6 by 28 by 28. Okay, 1 layer. Okay, now, so we usually would do this multiple times. And you can see that if we use the original idea, each time when you use a 5 by 5, it will be reduced by 4. From 32 to 24. 32 to 28, 28 to 24. Why? 4? Because filters 5 by 5 means that you're going to be moving until you reduce, you don't need to move all the way, right? You're going to reduce it by 4. So whatever the filter size you have, the size of this will be deducted, okay, will be reduced by your filter size minus 1. If you filter 5 by 5, then 30 will become 28. If your third filter here is 3 by 3, from 32, what's the next one? 30, because 3 by 3 means that you're going to lose 2. The size of filter minus 1 is going to be by lose 2. Okay, so therefore 32 will become to be 30. Okay, so the filter size, okay, is something that you can define yourself. Because in our programs, you can see that when you define your, sorry, let's come back to this, okay? When you define your layers, okay? Here you can see that we have convolution, 2D, right? I have the input size of something, and I have how many, 32 of this, okay? And my kernel size. Kernel size 5 here means I want to use 5 by 5 filter. Many of them also use kernel size to be 3. Sometimes kernel size could be 7, okay? But usually you don't want the kernel size to be too big. You want it to be kind of smaller because you want to capture, kind of enough, okay? And you have many different field layers that you will be able to catch, okay? But this is going to be one thing that you can see that here we use a kernel size of 5. Okay, later on we'll see that. Let me just look at this one here. This is another program trying to do the FashionNet, and let me see what kind of filters it uses. Okay, it has this batch size is 3. The filter size to be 3. Okay, so it's convolution layer. It's a 28 by 28. It's 32 different channels, and use the filter size of 3. Okay, to use 5 or use 3, which one is better? Nobody knows. That's why we want you to do the homework. In your homework, I want you to try different ones and tell us what do you think. Okay, and there are many different factors, but here you can see that even for the same job that people are designing in different ways. This one, both of them are using 2 layers, but you can definitely use 3 layers, you can use 4 layers, okay, whatever. Okay, and here you can see it's using 32, okay, to be the channels, okay, but you can design different ones. Okay, so here we get using 5 by 5, and then here we have 6 channels. So the output here will be 6, okay? And here we use 10 channels, meaning that I'm going from the simple RGB, and then next one I want to design 6 different features, okay, different type of things. But the next one I make it 10, okay, and I can make it to be, kind of different kind of classes, okay. So the number of channels again is something also that you can decide yourself, how many channels you want, okay. But in any case, we can put together many such layers, okay, and between the layers, okay, we also use ReLU, okay, so that because as we said that we don't want to use just the linearization, we also always want to use ReLU here to capture some important information and kind of forget something which is supposed to be a noise, okay. And then so if you have this is an example that if you have one original picture going through the convolution with a ReLU, you produce something like this. So it captures certain things. This is a plane, this is a car. It's becoming to be fuzzy, but for computer machine, so for the machine learning, actually, this is something probably had captured some features that is more important, okay, the global size or global shape rather than individual pixels, okay? And this is going through even more layers with even more pictures, and you can see that they are all trying to go into something. And so some of this, you can see roughly they are shape of car and shape of maybe birds or something or this and that, okay? And so people have tried to see that what each of layer has captured. This is actually use 64 filters. So therefore you can see there are 64 different type of output. Each of them is using 11 by 11 filter and using 3, because they're RGB, and so therefore this is the output, okay? And so even the AlexNet, they have tried different quote unquote such design of the models, okay? And this again is just some study, to see that using 3 different, sorry, not 3, 1, 2, 3, 4, 5, 6 different convolution layers, okay? After that, each of that with a ReLU, And then in the middle, they have the pooling here. Okay, I'll talk about pooling a little bit later. And then eventually, okay, I have the fully connected layer, and they are able to count to say, this one here looks like a car. Okay, that's the convolutional neural network. Okay, so, okay, so convolutional neural network, okay, CNN with the filters, with the layers, okay, actually you can imagine that it is going through this, things, okay, but you can also specify something which is called stride. Okay, stride means that every time when you move to the left or to the right or to down, you can go from the first location not always to the next location, but with certain distance, okay, or certain steps. So the first time you're here, next time if you have stride of 2, then you move to 2. Okay, so you will be moving faster. So you're not looking at so much detail, okay? But when you are moving to the stride of 2 or something, you need to be careful that sometimes that you may not be able to kind of evenly. So if you have stride of 3, then the first one will be here, next one will be here, and after that, then it has only one column to use, and there will be a problem. Okay, so so when you can calculate the stride, okay, design your system to do the stride, okay, you need to be careful, okay. And so that is something we can also do, is to expand your original picture with the padding, to say that in addition to the original picture, I put some extra zeros beyond your original picture, so that your stride will be able to and be run okay. So you can use this one here to say, okay, I'm going to add, with your some original picture with some zero pad, okay, then you will be able to have more. Okay, so all these are different techniques to be built in your convolutional neural network. Okay, you just need to be careful when you design this. Okay, your stride and also your padding. Okay, you know what kind of output size you're going to get. Okay, and there are many details, numbers. And one thing I want to say last is that using the convolutional neural network, using the multiple layers, actually, the information you can capture if you have multiple layers, actually, the information you can capture is going to be accumulation and as well as expansion of the area. Because here in your final output is here, but this EM1 is going to be produced using the information from this filter here. But this filter here, each of them, actually they have their own cell, and their cell actually coming from previous one, which is here. So even this single cell here actually is going to be capturing the information from here, and then eventually from the whole thing. Okay, so using small filter, multiple layers, is the same, just like you're using a large filter in one layer. Okay, so by using multiple layers, each with a smaller filter, you still will be able to have the result of capturing everything from a larger area. Okay, so that for large pictures, okay, we want to have, kind of more layers so that we'll be able to see the whole image. But of course, that you are going to be spending. When you have more layers, okay, you're going to be more effort, okay, and also the information is going to be quite a lot. So another thing we can also already talk about the stride, but the other thing I want to talk about very quickly is pooling. Okay, pooling is something that we have seen that the people have used that in the middle of their layers. Is that pooling sometimes allow us to say, even though I have some, output which is bigger picture, but I don't really need to have so much information. Then I can simply shrink the picture into something smaller. So this is using the idea of to say, for each of the area, okay, each of the cell here, I don't look at each one of them, but I'll simply take the whole, this square here, and then capture the information by saying that out of this 4, I will keep only the largest one. So 1, 1, 5, 6 here, I'll keep just 1, 6. 2, 4, 7, 8 here, I'll keep the 8, and this one here, I keep the 3, and this one here, I keep the 4. So I keep the largest value from here so that I have already caught, I have already gathered all the important information, but my data size can become to be smaller and which will be more efficient for me to process, okay, later on. Okay, mixed pooling is the one most often used, but you can also use some other different type of pooling to gather the information in the neighboring area to reduce the size of the information. Okay, so pooling is also something you can use, or you don't have to use, but it would help you to reduce the kind of the efficiency. Okay, so it is quite common for us to be designing a CNN with a convolution ReLU pooling. Okay, or in some of these examples we have seen that they have used convolution. Okay, then ReLU. Okay, the ReLU after convolution. Okay, and then after that there's pooling. Okay, and then you can see there will be another convolution, ReLU, and after that the pooling. Okay, so this is all different type of network that you can try to put together, and but these are kind of a very common form of the neural network that people have designed. Okay, I was going to try to ask Daniel to talk about our project. We don't have so much time. What should we do? Okay, let me just quickly go through this in case anybody have any question. Okay, so MNIST data set, okay, and also the fashion MNIST is something that we want you to look at, okay, and both of them, as I have already shown you in some of this, that I'm actually not coming up with many of this. So many of this actually I go to search, and so this is, for example, an example tutorial showing me how to actually build the MNIST with CNN. Okay, if you want, I can share this page with you, and I also have this example here, and this is a very simple one. I use this one because the structure is very easy to understand, very clean. Okay, and you put together all these hyperparameters together. Okay, so any case, what we have given you are 3 different notebook files, right? And so in the notebook file, there are a lot of to-dos. Okay, I want you to fill in. Okay, basically is to build the thing. Okay, and just follow the instruction. The first one is to try to train a single model. Okay, using both the MNIST and fashion MNIST data together, okay, to train, okay? And after that, then you simply test to see that what kind of loss you can get, okay, and as well. So this is not just, this is the epoch, right? Epoch, so just try to show that how your loss function is decreasing and how your accuracy is increasing, okay, for both data sets. Okay, for both data sets, but one model, okay, train using both data sets, okay, and then show us what your result and how you can improve, okay, the result. Okay, so I want you to try different ones, okay. If you want to change the different network, you can do that, or you can just tune the hyperparameters and see how you can do it. The second one is transfer learning. Okay, so transfer learning is to to kind of train one, okay, and then simply use that to test data from the other, okay, and then you can see that if you train using the MNIST and then test it with the fashion MNIST, probably is not going to do a very good job because they have never seen a T-shirt before, okay. But if you have trained a T-shirt and then ask, T-shirt and boots and this and that, you probably have more sophisticated knowledge. So when you give it some MNIST, just numbers data set, it can still produce a pretty good result, but not perfect. So I want you to try different one to see that how the result from the fashion MNIST can be used to test, for example, like the MNIST. Okay, and last one is to see that how you can try to retrain, fine tune. Is that fine tune? Okay, fine tune after you have built one model, and then can you use some data set, some input from the other data set, and then just to fine tune. You don't need to start from scratch, but try to fine tune it a little bit more. Okay, and so this one here is try to see that originally you use only the model which is trained for MNIST. Okay, and it probably doesn't know too much about T-shirt, and then you use some T-shirt data, and then try to improve it. Okay, and then hopefully that your system will be able to do better with a little bit of the training. Okay, so please go read the notebook. It has some explanation. But in this homework, okay, we are not just looking at your code, your result, but we also want you to tell us your strategy. Okay, your strategy, what you have tried, or how are you changing the parameter? Are you changing your things? This is something that is to be counted as 10% for each of them. Okay, so your code, your result will be total of 70, but your analysis, your report on your work is going to be something that will be, counted as your part of your grade. Okay, so I won't see you next week. Please try to do this, and the project is still at the end of November, right? I'm sorry, it's October. I don't remember the detail, but the last Thursday of the October. Okay. Any question you can send email directly to us by Teams or something. Okay, very good. That's the end for today.